Assalamu alaikum, brothers and sisters. Welcome to the journey of quest where we quench your thirst of knowledge. Our planet is a treasure chest, brimming with riches beneath its surface. These treasures are not gold or diamonds, not in the traditional sense. They are minerals, the building blocks of our world. From the towering granite peaks to the grains of sand on a beach, minerals are the silent architects of our planet's grandeur. They form the bedrock of our civilization, quite literally. We often take these earth materials for granted, unaware of the intricate processes that form them. Their journey through geological time is a tale of intense heat and pressure, of erosion and deposition, of transformation and rebirth. Understanding how minerals concentrate, how they cluster in specific locations, is key to unlocking the secrets of our planet's past and securing our resource future. Minerals are more than just rocks. They are naturally occurring, inorganic solids with a defined chemical composition and a specific crystal structure. This means that each mineral has a unique recipe of elements arranged in a specific repeating pattern. This internal order gives each mineral its characteristic properties. Take, for example, the mineral quartz. It is composed of silicon and oxygen atoms arranged in a tightly bound three-dimensional network. This structure makes quartz incredibly hard and resistant to weathering, explaining its abundance in Earth's crust. From the glass in our windows to the silicon chips in our computers, quartz is a versatile mineral with countless applications. Another example is halite, commonly known as rock salt. Its simple cubic structure with alternating sodium and chlorine atoms gives it its characteristic salty taste. Halite deposits, remnants of ancient evaporated seas, provide us with this essential mineral for food preservation and flavoring. The diversity of minerals is astounding, with thousands of known types, each with unique properties determined by their composition and structure. Some, like gold and platinum, are prized for their rarity and beauty. Others, like iron ore and bauxite, are essential for construction and manufacturing. Understanding these fundamental building blocks is crucial to appreciating the intricate tapestry of our planet. Mineral formation is not a random process. It is a symphony orchestrated by geological forces, with temperature, pressure, and chemical composition playing crucial roles. Just as a symphony has different movements, mineral formation occurs through various pathways, each leaving its unique signature on the final product. One of the fundamental processes is crystallization, where dissolved minerals in a fluid, like magma or water, solidify into an ordered structure. Imagine a crowded dance floor slowly emptying as couples pair up and crystallize into a structured pattern. This is analogous to how atoms and molecules arrange themselves to form the repeating lattice of a crystal. Another important pathway is precipitation, where minerals solidify directly from a solution due to changes in temperature or chemical composition. Think of adding sugar to hot tea. It dissolves readily, but as the tea cools, the sugar's solubility decreases and it precipitates out as sugar crystals. Minerals can also form through biological processes. For example, marine organisms like corals and shellfish extract dissolved minerals from seawater to build their shells and skeletons. Over time, these biological structures accumulate and solidify, forming vast limestone deposits. The formation of minerals is a continuous process, shaping and reshaping our planet's surface and interior. Understanding these processes is key to unraveling the geological history of Earth and predicting where valuable mineral deposits might be found. Crystallization is a captivating process, a testament to nature's ability to create order from chaos. It is the process by which atoms or molecules arrange themselves in a highly ordered repeating pattern, forming a solid with a distinct geometric shape. This internal order is what distinguishes crystals from amorphous solids like glass, which lack a regular atomic arrangement. Imagine a salt crystal, a perfect cube with sharp edges and smooth faces. This geometric precision is a direct result of the orderly arrangement of sodium and chlorine ions within the crystal lattice. Each ion is surrounded by its neighbors in a specific configuration, dictated by the chemical bonds holding them together. The process of crystallization begins with a supersaturated solution, where the fluid, be it magma or water, contains more dissolved minerals than it can hold at a given temperature. As the solution cools or evaporates, the dissolved minerals become less soluble and begin to precipitate out, forming tiny seed crystals. These seed crystals act as nucleation points, attracting more dissolved minerals from the surrounding solution. As more and more atoms or molecules attach themselves to the growing crystal, It develops its characteristic shape, reflecting the internal arrangement of its constituent particles. The size and perfection of a crystal depend on factors like the cooling rate, the availability of space, and the presence of impurities. Deep within Earth's fiery interior, a different kind of crystallization takes place. Molten rock, known as magma, slowly cools and solidifies, giving rise to igneous rocks and the minerals they contain. This process, known as igneous crystallization, is responsible for some of the most familiar and economically important minerals on Earth. Imagine a volcano erupting, spewing forth molten lava that flows down its slopes. As the lava cools and solidifies, it forms extrusive igneous rocks, like basalt and rhyolite. The rapid cooling of lava at the Earth's surface results in fine-grained rocks with small crystals, often too small to be seen with the naked eye. In contrast, intrusive igneous rocks like granite and gabbro form when magma cools slowly beneath the Earth's surface. The slow cooling allows crystals to grow larger, giving these rocks their characteristic coarse-grained texture. The specific minerals that crystallize from magma depend on its chemical composition, which varies depending on its origin within the Earth's mantle. As magma cools, different minerals crystallize at different temperatures, a process known as fractional crystallization. This sequential crystallization leads to the formation of rocks with varying mineral compositions, even if they originate from the same magma source. For example, a single magma chamber can give rise to both granite, rich in quartz and feldspar, and gabbro, rich in pyroxene and olivine. Water, the lifeblood of our planet, is also a master sculptor of minerals. Through erosion, transportation, and deposition, water plays a crucial role in the formation of sedimentary rocks and the concentration of valuable mineral deposits. These processes, driven by the relentless forces of wind, rain, and ice, shape our landscapes and provide us with essential resources. Imagine a rushing river, carving its way through a mountain range. As the water flows, it erodes the surrounding rocks, breaking them down into smaller and smaller particles. These particles, along with dissolved minerals, are carried downstream, where they are deposited in layers, forming sedimentary basins. Over time, these layers of sediment are buried and compacted by the weight of overlying material. The pressure squeezes out water and air, while dissolved minerals precipitate out, cementing the sediment particles together, a process known as lithification. This transformation from loose sediment to solid rock is the hallmark of sedimentary rock formation. Sedimentary processes are responsible for concentrating a wide range of minerals, including fossil fuels like coal and oil, evaporites like gypsum and halite, and even precious metals like gold and uranium. Understanding these processes is crucial for locating and extracting these resources responsibly. Deep within the Earth's crust, where temperatures and pressures soar, rocks undergo a remarkable transformation. They are no longer content with their original form, whether igneous, sedimentary, or even previously metamorphosed. Under the influence of heat and pressure, they embark on a journey of metamorphosis, rearranging their mineral assemblages and transforming into new rock types. Imagine a mountain range forming as tectonic plates collide. The immense pressure and heat generated during this process can transform existing rocks into metamorphic rocks like slate, schist, and gneiss. The original minerals in the parent rock recrystallize into new minerals that are stable under the high-pressure, high-temperature conditions. The degree of metamorphism depends on the intensity of heat and pressure experienced by the rock. Low-grade metamorphism, characterized by relatively low temperatures and pressures, may only slightly alter the original rock's texture and mineral composition. In contrast, high-grade metamorphism, occurring at greater depths and temperatures, can completely obliterate the original rock's features, creating new minerals and textures. Metamorphic processes are responsible for concentrating a variety of minerals, including gemstones like garnet and emerald, industrial minerals like asbestos and talc, and metallic ores like copper and zinc. The intense heat and pressure associated with metamorphism can mobilize and concentrate these minerals, making them economically viable to extract. Erosion, often seen as a destructive force, is also a master concentrator of minerals. Like a giant sorting hat, it separates the valuable from the mundane, concentrating specific minerals in placer deposits, residual deposits, and secondary enrichment zones. These processes, driven by wind, water, and ice, play a crucial role in making certain mineral resources economically viable. Imagine a swift mountain stream carrying a mix of sediment and heavy minerals eroded from the surrounding rocks. As the water flows over a gentler slope, its velocity decreases, and it loses its ability to carry the heavier minerals. These minerals, often including gold, platinum, and diamonds, settle out of the water and accumulate in placer deposits along the streambed. Residual deposits form through a different process, where weathering and erosion remove the less resistant minerals from a rock, leaving behind a concentration of the more resistant minerals. For example, bauxite, the principal ore of aluminum, forms through the weathering of aluminum-rich rocks in tropical climates. Secondary enrichment zones form when groundwater leaches and redeposits minerals, concentrating them in specific areas. This process often occurs in areas with sulfide mineral deposits, where weathering and oxidation create acidic groundwater that dissolves and transports metals like copper, silver, and gold. These metals can then precipitate out of the groundwater in more concentrated forms, making them easier to mine. The journey of minerals from Earth's depths to our everyday lives is a testament to human ingenuity and our reliance on Earth's resources. From the initial exploration and discovery of mineral deposits to the complex processes of mining, processing, and manufacturing, we have developed sophisticated techniques to extract and utilize these valuable materials. Mineral exploration involves a range of methods, from traditional geological mapping and prospecting to advanced geophysical techniques like seismic surveys and aerial magnetic surveys. Once a potential mineral deposit is identified, drilling programs are conducted to assess its size, shape, and grade, determining its economic viability. Mining methods vary depending on the type of deposit, its depth, and its location. Surface mining techniques like open-pit mining and strip mining are used for shallow deposits, while underground mining methods like shaft mining and longwall mining are employed for deeper deposits. Each method comes with its own set of environmental and safety considerations. After extraction, the raw ore undergoes processing to separate the valuable minerals from the waste rock. This often involves crushing, grinding, and separating the ore based on differences in physical properties like density, magnetism, or surface chemistry. The concentrated minerals are then further refined to produce metals, chemicals, and other materials used in various industries. Our exploration of Earth's mineral treasures reveals a profound truth. We are inextricably linked to our planet and its finite resources. Understanding how minerals form, concentrate, and are ultimately utilized is not just a matter of scientific curiosity, but a shared responsibility. This knowledge empowers us to make informed decisions about resource management, environmental protection, and the sustainable development of our technological civilization. As we delve deeper into the Earth's crust, extracting the minerals that underpin our modern lives, we must do so with a sense of respect and stewardship. We must minimize our environmental impact, ensuring that mining operations do not irrevocably damage ecosystems or compromise the health of local communities. Furthermore, we must embrace the principles of resource conservation and recycling. By using minerals more efficiently, reducing waste, and developing innovative recycling technologies, we can extend the lifespan of these finite resources and reduce our reliance on new mining operations. Ultimately, our understanding of Earth's mineral wealth should foster a deeper appreciation for the intricate workings of our planet and the interconnectedness of all living things. By embracing a sustainable approach to resource utilization, we can ensure that future generations inherit a planet as rich and vibrant as the one we enjoy today. Thanks for watching us share our videos. Subscribe our YouTube channel and press the bell icon and stay curious for new uploads.